Hello everyone, welcome to this video. In this video, let's answer this question that do these two different cosets, one is generated by A, another one is generated by B. So AH and BH, do they have any element in common? If so, what is that element, right? So this is the question that arises here in our mind. So let's have a look here at this result. So we can say that the two cosets of H, this is a very powerful and important result. Why? Because it tells us exactly what is there in between AH and BH. So either this AH and BH, they are identical to each other, or they do not have any element in common to each other. So that means either they have all the elements in common to each other or none. So this is the result. So here property 6 tells us exactly that. So here we say either AH is equal to BH or their intersection is empty. So that means they do not have any element in common to each other and hence they are disjoint to each other. For the proof here, if AH intersection BH is empty, then we are done and the result is proved. So suppose that this thing is not empty, right? So this is what we have done. So if this is not empty, so it would definitely contain some element. Let's call that element as C. So let C belongs to AH intersection BH. So that means this C would be a member of AH and the C would be a member of this BH as well. So according to the property that we have studied, the elements AH is equal to BH if and only if A is a member of BH. Now this is we have this thing that C is a member of AH, so that means CH would be equal to AH from this result, and moreover because C is a member of BH, so CH would be equal to BH. Now CH is also equal to AH, it is also equal to BH, so both AH and BH, they should be equal to each other. So that is what we are saying. We have CH is equal to AH and CH is equal to BH, so both AH and BH, they are equal to each other, right? So either this is empty, their intersection of AH and BH, that is empty. If it is not empty, if it has some elements, then all the elements are common in between them. Then both of the cosets has to be equal to each other. So this is the result here. Okay, in a similar line, can we know how many elements are present in this AH and how many elements are present within this BH, or do they have different elements in different cosets? So let's answer this question by our next property. The next property tells us that okay, before moving on to the next property, few things should be noted here for this property. It tells us that a left coset of H is uniquely determined by any of its element. Now you see, because of this property, if A is contained in BH, then it is AH is equal to BH and it represents. So that means this BH can be represented by any of the coset where this coset BH contain an element A within it. On a similar ground, we can say that the left coset of H is uniquely determined by any one of its elements. So this is the same thing, and in particular any element of left coset can be used to represent the coset. So this also tells us the same thing, that if you take from the given coset, if you consider one such element, then you can use this element to construct another coset which is equal to, suppose this is AH, which is equal to the given coset. So this is what they are saying here, correct? Okay, moving on to the next property, we wanted to determine whether the number of elements in AH, they are equal to the number of elements here, or they are different, and if different, what is the number and how we may find it. So let's have a look here at the next property. It tells us that the number of elements in the coset AH and the coset BH, they are equal to each other. So that means all the left cosets of H, they have the same size, correct? So the proof is also very simple. So in order to prove that the order of AH is equal to the order of BH, the number of elements, they are same within this, we need to prove that if we define a mapping from AH to BH, then we need to prove that that mapping is 1 to 1. So let's call that mapping as phi, which is defined from AH to BH, right, such that phi of AH is equal to BH. Then we need to prove that if this mapping is BH, so it is taking AH to BH, right? If we cancel out this H with this H, so A is taking to B, so that means for all the A we have some B here, so that means the mapping would be 1 to 1 according to the cancellation property, and because for each element here we have some element here, so therefore the number of such elements would be the same in both the cosets, and this is what we wanted to prove here. So in mathematical terms, if phi is such mappings such that phi of AH is equal to BH, then it is 1 1 because according to this 1 to 1 calculation, we can clearly see it is 1 1. So each element A is mapped to B. So the number of each such element A is equal to the number of each such element B. So that means the number of elements which are present in the coset AH is equal to the number of elements which are present in the coset BH. So I hope you understood these properties well. Well, that is it for this video. Thank you for watching.